This classification is about the means by which the wave is propagated from one point to another. So, ways by which waves are propagated or transmitted. This classification seeks to investigate how particles vibrate, and when particles vibrate, how the wave is also transmitted or propagated. So this is about vibration of particles and propagation of wave. Propagation of the wave. Now, progressive and stationary wave. This classification of wave also looks at how the energy is transmitted within the material or the medium. For progressive wave, energy is continuously propagated within the medium. Okay, and then for stationary wave, the energy is propagated or transmitted only within a section of the medium on certain conditions, which we'll later see. Okay, so this one seeks to investigate how the energy is propagated. Is the energy continuously propagated within the medium, or the energy is propagated at a section part of the medium based on certain conditions or factors? Okay, so let's take this one, progressive wave, and look at what it's about. We define progressive wave as any wave that can be transmitted from one region of a medium to other regions or other areas of the same medium. So, a progressive wave is a wave that can continuously be propagated from one region of a medium to other region. This region here refers to area. Okay. Progressive wave comes about whenever a medium it's so large or wide, then progressive wave comes to play. So example, you see, look at the ocean, where I said the ocean wave is formed as a result of the splashing of wind energy on the surface of the ocean. Look at the region or the area where the wind splashing starts. Okay, now the wind speed is actually very huge at the mid part of the ocean. So when it blows there, the energy of the wind is transferred to the water molecules and transferred on and on and on till it dies out at the seashore. So here we are looking at a very vast water medium, large water medium. And so when the medium is very big or large, progressive wave is formed. Then the energy can be transmitted or propagated on and on and on continuously throughout the medium. So progressive wave is formed when the medium is so large or big or wide. Please, is that okay?
Yes, please.
All right. Now, what about stationary wave? As for stationary wave, the medium must be very small. The medium should not be very wide as progressive wave. We must have we must have a smaller medium. Okay. Now, all string instruments, musical instruments, operate on the principle of stationary wave. And we define stationary wave as, let me give you the definition of for a stationary wave is formed whenever two waves, two progressive waves of the same amplitude frequency and wavelength. So a stationary wave is formed whenever two progressive waves of the same amplitude, frequency, and wavelength. So instead of frequency, wavelength, and traveling from opposite directions interfere. Meaning the two waves must be traveling from opposite direction. Interfere. Okay. So whenever two waves of this characteristics, please, in defining it, do not forget these three characteristics. The two waves traveling from opposite directions must have the same amplitude, frequency, wavelength, and must be coming from opposite directions. And their interference creates the stationary wave. Okay, so let me give you a diagram of how progressive wave looks like, and then how a stationary wave or standing wave is also like. So whenever you have a very vast medium, and the wave is initiated somewhere. So long as the medium is so big or large, you create a stationary wave. Sorry, a progressive wave. But when the same medium is this time shortened or reduced, so we have, how do we reduce or minimize the medium? We minimize the medium by creating a barrier or a boundary along. So example, if I create a barrier here, what happens is that this incident wave hits the barrier and then reflects. So whenever you create a barrier within or a boundary within a very large medium, what happens is that the incident wave, the first progressive wave, travels, hits the barrier, and then reflects. When this happens, it creates the two waves interfere, creating a stationary wave. You realize that this is the incident wave. The incident wave. And this is also the reflected wave. Okay, so the incident wave, then the reflected wave must have the same amplitude. So the amplitude from the equilibrium position X to the crest A must be the same as the amplitude of the reflected. Hence, of the same amplitude, now frequency. 1, 2 complete waves here. Then 1, 2. So the same frequency, the same wavelength. From this point, there's the wavelength, and the reflected must also have the same wavelength as the incident. That is. So practically, stationary wave is formed when you create a barrier. Okay, the practical application of this is, you see, the guitar string. I said all musical instruments operate on the principle of stationary waves. So the musical instrument is such that there are, especially the guitar, there are 5 strings. This end is tied. One end of the string is tied. The other end is also tied, creating a boundary or barrier. Okay, so whoever plays it just plugs the strings, and by plugging the strings, you are causing a vibration. So the incident wave hits the boundary and then reflect. So all musical instruments, whether string instruments, wind instruments, pipe instruments, all operate on the principle of stationary waves. Please, are we okay? Are we okay?
Yes, please.
Is there any question? If you have any question to ask, Akuya Adoma, Josephine, Inshira, Gerard, Oye, Nanama.
Sir, please, I have a question.
Okay, ask.
So when you said the stationary wave is supposed to be 2 progressive waves, which is reflected. So not necessarily that it's supposed to be like 2 actual waves, supposed to be just an incident and a reflected one.
So by definition, this is how we define it. When 2 waves of the same amplitude, frequency, wavelength traveling in opposite directions interfere. But practically, this is how it must be done. When you have a medium, you must create a barrier or boundary so that an incident wave, when you create an incident wave, it will hit the boundary and reflect. The interference of the incident and then the reflection creates the stationary wave. So practically, that is what it is done. But when we are defining it, it is defined as if, oh, when you send one wave from this direction and another from this direction. Do you get it?
Yes, please.
All right. Okay, so we will go into each one of them one at a time. So let's look at the progressive wave. So the progressive wave is also known as a traveling wave. It's also known as the traveling wave because it is propagated from one region of a medium continuously to the other areas or regions of the medium. So wave itself is denoted as a sine function. So this is the displacement so this indicates a progressive wave. So long as the medium is so big, it will go on and on and on in that manner. So let's take X to be the equilibrium position, okay, the rest position of the wave. I'm coming, please. Now, from the equilibrium position to a position of crest, we have the amplitude. So this is the amplitude. And yesterday, last time we saw that the amplitude of a wave indicates the what? The amplitude of a wave indicates the wave's what? Yes, anybody? Ekuya, Ajoa, and Co. Inshira, the amplitude of a wave determines what?
Simply the maximum displacement.
Amplitude is the maximum displacement, but the amplitude of a wave determines what? I told you, I said
the energy.
The energy carried by the wave.
The energy.
Yes. So if you want to determine the energy carried by a wave, you must, a measure of the amplitude determines the energy. So from, this is also the same amplitude. Okay. So this is a progressive wave. Now let's determine, so graphically, if you want to indicate how a wave looks like, you must draw something like this, a sine function to indicate the wave. Let's look at the mathematical equation which can be used to represent a wave. Don't forget, in mathematics, in your mathematics lesson, if you draw something like this, you say that this is a straight line, okay? And mathematically, a straight line is represented by this equation, mx plus c. So the graph represents the straight line, and then the mathematical equation also explains it further. A wave, anything wave is like this. So this is the graphical representation of a wave. What is the mathematical expression to represent a wave? A wave is a sine function. So it's a harmonic motion. And the displacement function of a body executing simple harmonic motion is represented as y is equal to a sine omega t, sometimes plus or minus phi. So this is the displacement equation of a body. Displacement equation of a body executing SHM. Now, since a wave is also a harmonic function, a repeated function, the equation of a wave, a progressive wave, is also represented by or indicated by the displacement function of a wave. So this sinusoidal thing can also be represented by y is equal to a sine omega t plus or minus phi. Okay, meaning that the displacement function of a body executing SHM is the equation for a progressive wave. Now, if the wave starts from the origin, okay, in simple harmonic motion, when the motion just starts from the mean point, y is equal to, the displacement equation is given by y is equal to a sine omega t. So this indicates that the wave, simple harmonic wave or function, starts from the origin. Start from the origin. Now, if it doesn't start, if we are not picturing the wave to be starting from the origin, but we are looking at a wave, a particle vibration at a certain distance away from the origin, such as this, a vibrating particle P, and P has a distance of x from the origin. Okay, meaning it is like I am at the origin and I'm picturing a particle vibrating ahead of me. Okay, so we are picturing this particle, vibration of a particle P at a distance of x from the origin. Okay, now the equation for a vibrating particle P from the origin is that, you see, before we write the equation, if we are actually picturing a particle over here to be vibrating, then in terms of length of this wave, we are saying that the length of this wave, particle vibration, the particle vibration actually creates the wave. So this particle vibration is at a distance of lambda wavelength from the origin. So the distance from O to a particle, let's say Q, vibrating here is equal to lambda. So x is equal to lambda. Now this particle vibration P, we don't know its wavelength. The reason for which we are representing this by x. Please, is that okay? Is it understood? Let me change my speaker and then get back to you, okay? So give me a minute or two. I think the battery has gone down, so I'm coming. Recording. If we want to write displacement equation for a vibrating particle P, the displacement equation for a vibrating particle P. You see, in terms of vibration, when the wave starts, the wave will start from the origin before reaching the particle P to vibrate. It is like the wave is moving from left to right. So in terms of vibration, a particle at the origin is vibrated before reaching the particle P. So in terms of vibration, the point O leads P. Okay. In terms of vibration, a particle at O vibrates before P. So we can say that O leads P in terms of vibration. Please pay attention and listen to the technicalities very well. So if we are writing equation for P, don't forget equation for O is this. A particle O vibrating at the origin. This is it. Now, if you are writing equation for a vibrating particle P, because O leads P, then you have to subtract the phase angle of P from O, because O leads P. O vibrates first before P. So if you want to write a displacement equation for P, you must subtract the phase angle of P from O. The reason is that O leads P in terms of vibration. So because O leads P in terms of vibration, displacement equation of P becomes this. So let's just write the equation and see how we use the equation. So Y will be equal to, we are going to subtract the phase angle of P from O. So Y is equal to A sine O is equal to omega T theta. Let me go by systematic. So theta minus the phase angle of P, which is phi. And I am repeating, we are subtracting the phase angle of P from O because O vibrates first before P. So let's expand this equation. Y therefore will be equal to A sine theta is omega T minus phi. So this becomes the displacement equation or the wave function of a particle P vibrating at x distance from the origin. Please, is there any question? Is there any question here?
No,
Yes,
sir.
sir.
Because we are going to expand the equation. So we have just identified that the displacement equation of a vibrating particle P, which is x distance from the origin, is equal to this. Y is equal to A sine omega t. Y is equal to A sine omega t minus phi. Now we are going to expand this equation. When we use ratio and proportion, we could see that phase angle 2 pi is to wavelength of lambda. Okay, so the phase angle thing is this. Now, I want to explain the phase angle again. A particle at the origin has an equation this. In fact, in simple harmonic motion, this positive pulse, let me draw it well. This positive pulse represents an angle of 180 or pi. Then a full cycle represents an angle of 360, which is 2 pi. So a particle at O, the phase angle is 0, meaning we are just starting from the origin. So there's no phase difference between a particle at the origin. That is why the equation is y is equal to A sine omega t. Here phi is 0. So when you add plus or minus phi, this is 0. So it will come back to this. Okay. But if we are looking at a vibrating particle over here, let's assume this is a particle V here. Then when you compare a particle vibration at this point to the origin starting point, the angle between the origin and a particle V vibrating is equal to 180. 180 is also equal to pi. So it means the phase difference between the origin and a particle vibrating at this point, the phase difference is pi. So it means pi is equal to pi. So when you are writing it for a vibrating particle at this point, then it should be y is equal to A sine omega t minus pi. And this becomes the equation of the particle V vibrating at this point. Nanama, are you okay? And as I said earlier, we subtract because a particle at the origin will vibrate before a particle V over here, because the wave is moving from left to right. So for X, a particle P here, we don't know this phase angle. That is why the phase difference between the origin and this point, that is why we say let that be equal to phi. Phi is just a letter to represent the phase difference between the origin and the position of vibrating of the particle. All right. So if you are writing the equation for the particle P vibrating, then y will be equal to A sine omega t minus its phase difference, which we don't know, phi. Okay. Now what we are going to do is expand this equation. Now, a particle vibrating here has a wavelength of lambda. So lambda is to a phase difference of 2 pi. This corresponds with a phase difference of 360 or 2 pi. But x also corresponds to an unknown phase difference, phi. Let's take ratio of what we have. So lambda over 2 pi is equal to x over phi. Then let's make phi the subject. Okay, help me make phi the subject. Okay, Adoma, from what we have on the board, help me make phi the subject. Okay, Adoma. Hey, is Akuya there?
Phi is equal to lambda.
You are making phi the subject. Okay, Josephine. Josephine, take over. Help me make phi the subject.
Yes, I have phi to be x.
Just cross multiply and make phi the subject. Hey, you are wasting time. Oh. So when you cross multiply, you have this time this is equal to 2 pi times x. Therefore, phi is equal to 2 pi over, you divide 2 by lambda, lambda times x. So from this ratio and proportion thing, if you make phi the subject, this is it. Then let's substitute this into the general equation. You then have y is equal to a sine omega t minus 2 pi. Before we substitute this in, this component, which is 2 pi over lambda, is equated to a variable k. And this variable k is known as the wave number. Wave number. So we equate 2 pi over lambda to k, which represents wave number, the number of waves passing within a given time, k. Okay, so when we substitute whatever we got for phi, we have 2 pi over lambda times x. But because 2 pi over lambda is equal to k, we can further write this equation as y is equal to a sine omega t minus k x. This is the displacement equation of a wave of a particle p vibrating ahead of the origin. So this is the wave equation of a vibrating particle P. So whenever you are asked to write equation for a vibrating particle P ahead of the origin, this is it. the equation implies that this wave is moving from left to right. From left to right, or moving towards the positive x-axis. So this equation shows that wave is moving from right to left. Sorry, left to right, rather. Left to right. All right. Now we can further express the displacement, the wave equation in different forms. So we are going to look at the different ways of expressing the wave equation. Different ways of expressing the wave equation. So the basic form is that for a wave traveling from left to right, or from the negative x-axis to the positive x-axis, the equation is given by y is equal to a sine omega t minus kx. So the minus indicates that wave is moving from left to right. Let's look at the expansion. How expanding the progressive wave equation in different forms. So the first form is this. A sine omega t minus kx. And note that if there is a phase difference, then it means it doesn't start from the origin. If this is minus, then it means the wave is from left to right. Okay. The second progressive wave equation is that omega is equal to 2 pi over t, which is also equal to 2 pi f. And k, which is the wave number, is equal to 2 pi over lambda. So when you substitute omega and k into the progressive wave equation, you have y is equal to a sine 2 pi f t minus 2 pi over lambda times x. Now you realize that 2 pi is common, so you can factorize that out. So you have a sine 2 pi out ft minus x over lambda. This is another form of the second form of progressive wave equation 2. So this is 1, 2. Now the third form of progressive wave equation is this. We know velocity or speed of a wave to be equal to f times lambda. So let's make f the subject here and substitute it into this equation. So f is equal to v over lambda. Hey, Oye, you suffer a lot in writing lambda. Try and master it. So if f is equal to this, then when you substitute it here, you have y is equal to a sine 2 pi out. You have v over lambda VT minus X over lambda. And we can still pull out lambda. So we have Y is equal to A sine 2 pi over lambda out Vt minus X. This is a third form of progressive wave equation. A third form of progressive wave equation. Then the last possible form which we can possibly write is that we have F is equal to 1 over T. So come and substitute it into this one, into equation 2. Then you have Y is equal to A sine 2 pi 1 T over big T. Here we have 1 times T over big T minus X over lambda. And this is a fourth form of progressive wave equation. So these are the different progressive wave equations we can write. Okay. So when you see a minus, meaning there's a phase difference from the origin, then it means that the wave is moving from left to right, or moving from the negative x-axis to the positive x. Okay. Then you can use the already expressions we know. V is equal to F lambda. Omega is equal to 2 pi over period, or 2 pi F, to expand it beautifully. Please, if you have any question, quickly ask before we continue. Is there any question? Ishra, is there any question?
No, please.
Okay. So please, you must spend time to sit on the different forms of progressive wave equation written and then master. Okay, it's deriving it is not difficult, but you need to sit down to master. Now please, I'm coming in. Give me a minute. I'll be with you. The minus is an indication that the wave is Mami, Nana, I'm looking at your question. I'm coming. Yes, I'm going to look at explain the other part. So if this is minus, you see the operator at the middle can be you see the difference between small t and big T is that the displacement equation is actually y is equal to a sine omega t. All that we are doing is that we are expressing the displacement in terms of time. This same equation can also be written as a sine, because omega is equal to 2 pi over t times small t. So the difference is that we are looking for displacement as against any time t. So at any time t, we can calculate for the displacement or the wave function, the displacement of the wave. But the big T represents a specific time. And this specific time is the time taken to make one complete oscillation. Okay, so the small t is due to the fact that we are expressing the displacement of the wave in terms of at any time t. So at any time t, we can calculate for the displacement. But within the formula, we need to take account of that specific time, which is the period. The reason why we have small t and big T. All right. So when the wave, the phase difference can actually be plus or minus. The phase difference can be plus or minus. When it is minus, then it means the wave is moving from left to right, or moving from the negative x-axis to the positive x-axis. Then when it is plus, what it means is that the wave is moving from right to left. So let me write two equations to explain this. So when you have this, a sine omega t minus kx, wave is moving from left to right. There's the direction, or from the negative x-axis to the positive x-axis. Then when you have this, y is equal to a sine omega t plus kx. Then there's the direction of the wave. The wave is moving from right to left, or moving from the positive x-axis to the negative x-axis. Over here, you see, in writing the first equation, we considered a particle P vibrating. So we realized that a particle at the origin will vibrate before P. Okay, so in terms of vibration, if you are writing an equation for P, then we must subtract the phase difference of P from O. That is why we subtracted. So this phase difference subtracted from the origin. Now, if the wave is moving from right to left, this time, because the wave is coming this way, particle P vibrates before it gets to the origin. That is why we are adding. Because P this time will vibrate before O, the reason why we are adding the two phase angles, okay, phi to omega t. So when it's positive, then the wave is moving from right to left. If the phase difference phi is equal to 0, then the wave just starts from the origin. That is basically what it means. Please understood? Oh yeah, Josephine, Israel and Co, are you okay? Hey, are you people there? No one is
Yeah.
okay. Let's look at how to use the progressive wave equation in solving problems. How do we use the progressive wave equation to solve questions? How do we use the progressive wave equation to solve problems? So a wave is represented by the equation y is equal to a. So a is 7. 7 sine into brackets 40 pi t minus 8 pi x, where y is in meter. So where y is in meter. Find I, the amplitude. I, the frequency. I, the period. IV, the wavelength. Then V, the speed. Then VI indicates direction of wave. Direction of wave. So this is the question. This is the question.
Sir.
Yeah, all right.
Sir.
Hello.
Please, can you raise the camera a little so I question?
Raise it. Is it? I hope it's
Sir,
okay.
it's okay. Yes, sir.
Adjo, are you there?
Yes, please.
Inshira.
Yes, please.
Oye. Yeah, roll call.
Yes, please.
Josephine.
Yes, please.
Okay. Hey, Immaculate. Immaculate, you know, she has gone to sleep. All right, so let's see how we can solve this. So, in solving this, what you do is that this is the main question given to you. The main progressive wave equation given to you. Y is equal to 7 sine 40 pi t minus 8 pi x. So you compare this to the general progressive wave equation. Okay, so the general progressive wave equation traveling from left to right, and I'm talking of left to right because this operator here is a minus. So it means that The wave is moving from left to right. The question even asks it. That's the last question. So the general one we derived was y is equal to a sine omega t minus kx. So you compare a, which represents the amplitude, is equal to 7. So straight away that answers I. And I, which is the amplitude, A is equal to 7. And don't forget, we were told that y is in meter. So any measurement of length here should be in meter. So the amplitude is equal to 7 meter. Then II, frequency. Frequency can be, so it also means that this part can be compared to this part. Or omega is equal to 40 pi. Got TT, they will cancel out. So omega is equal to 40 pi. We are just comparing the given equation to the general progressive wave equation. So, and because omega is equal to 2 pi f, we equate 2 pi f to 40 pi, and we can easily find f. It should help me determine f. F will be equal to what is f? Oh, Ishra is gone. Okay. Oye, is that f is equal to what? Okay. So f is equal to 20 hertz. Then period. As for period, because T is equal to 1 on F, knowing F, you can also determine the period. So this will also be 1 on 20, which is equal to 0.05 seconds. Then the fourth one, IV, the wavelength. Wavelength, we equate kx to, or even k, because x will cancel out. K, we equate k to 8 pi. And because k is equal to 2 pi over lambda, we can determine lambda out of it. Adwa, what is lambda? Help me determine the value of lambda. Adwa? Otubia?
Yes, I had 104,
Yes.
0.25.
Lambda is equal to 1 on 4, which is 0.25 meter. Then the speed. Please help me calculate for the speed. Josephine, the speed is for you. Do it with speed. The rest of you should also do it. If Rooney also
Yes,
had, pardon?
Yes, I had 5 meter per second.
5 meter per second. Let's see. V is equal to F lambda. We can simply use this one. If F is 20 and lambda is 1/4, then this will be 5 meter per second. So this is how to solve questions in progressive wave equation. Another way of doing the same thing is that, you see, we derived several equations. And then the last question, indicate the direction of the wave. Once this is negative, then it means it is moving from left to right or moving from the negative x-axis to the positive x-axis. Okay. Okay. I want to draw your attention to the other way of solving the same question. The amplitude, as for the amplitude, there's no other method. You compare the given equation to the progressive wave equation. But look at the frequency. We had y is equal to a sine omega t minus kx. Then a sine omega is 2 pi ft minus 2 pi over lambda x. So when we compare this with y is equal to 7 sine 40 pi t minus 8 pi x. As for frequency, the fundamental one will do 2 pi f is equal to 40 pi. Then we find f. But the period, we can determine the period this way. Y is equal to a sine 2 pi ft minus 2 pi over lambda x. And we know f to be equal to 1 over t. So instead of f, let's put in 1 over t. So, we have 2 pi over big T times small t. Okay, so let's compare 2 pi on big T to 40 pi. Pi, 2 goes into SL1, 2 goes into 40, 20. So we have 1 over T equal to 20. T therefore is equal to 1 over 20. And that will also give us the wavelength. As for wavelength, once we have represented this by k by 2 pi on lambda, we compare. So 2 pi on lambda is equal to 8 pi. Then lambda therefore will be equal to 2 pi over 8 pi, which is equal to 1 over 4, aka 0.25. Then the speed. Look at the speed. Look at the speed question. Y is equal to 2 pi ft minus that. But we know Vf to be equal to V over lambda. So instead of F in the equation, let's put V on that. So we have Y is equal to A sine 2 pi V on lambda t minus 2 pi over lambda x. So equate 2 pi V on lambda to 40 pi. to 40 pi. This pi will cancel this. 2 goes into 40, 20. So we have V on lambda equal to 20. Therefore, V is equal to 20 times lambda. And we've found lambda. Lambda is 1 on 4. So 20 times 1 on 4 would give us 5 meters per second. So these are other different ways of doing the same thing. Please, is that clear? All right, your own question. Your own question, which you will try now. So please get ready and put that down. A plane progressive wave has amplitude of 3 meters and frequency of 150 hertz. And the velocity of the wave is 220 meters per second. And the velocity of the wave, or the speed of the wave, is 220 meters per second. Write down the wave equation, the progressive wave equation. So here you are to write down the progressive wave equation.
So the velocity.
So the velocity is 220 meters per second. So a plane, I'm taking it again. A plane progressive wave has amplitude of 3 meters and a frequency of 150 hertz. And the velocity of the wave is 220 meters per second. Write down the equation of the progressive wave. Write down the equation of the progressive wave. All right, start work. As we discussed, you compare it with what you have done. Okay, so the amplitude A is equal to 3 meters. Then the frequency is 100 and A is 3. Frequency is 150 hertz. Then the speed or the velocity is 220 meters per second. And we have to write down the wave equation, the progressive wave equation. So y is equal to a sine omega t plus or minus kx. In fact, a wave is such that usually, if it is not otherwise stated, its propagation is always from left to right towards the positive x-axis. So unless otherwise stated, it is a progressive wave is always written as omega t minus kx. However, if you write it as plus or minus kx, you are also not wrong. So if we have f to be this velocity, then we can easily calculate for omega. Omega will be equal to 2 pi f. So we have 2 pi times the frequency, which is 150. Therefore, we have 300 pi for omega. Then K is equal to 2 pi over lambda. And once we have frequency and velocity, we can find lambda. Lambda will be equal to V over F. V is 220, F is 150, giving us lambda to be equal to 22 on 15. Therefore, K is equal to 2 pi over 22 times 15. And so this is 30 pi on 22. We can further break this down to still 15 over 11 pi. Okay, then we substitute it into the equation. Y therefore is equal to A, which is 3 sine omega. We have 300 pi minus K is this 15 over 11. So 15 over 11 x. I omitted the distance. Then we can further play around this. Okay, or 3 sine 300 pi t minus, what is 15 divided by 11? 1 point what? 15 divided by 11.
1.364.
And this is the progressive wave equation. So exactly in the book, what we have in the book is y is equal to 3 sine, okay, bracket open, 300 pi t minus 1.36. Oh, where is the pi? Oh, okay. This is 15 over 11 pi. This is pi x. So we have pi times x. And that's the progressive wave equation. How many of you got this correct?
Mr. Dean,
Hello?
are you supposed to leave it in like the original equation?
No, you are writing an equation which looks like this, which is similar to the general progressive wave equation.
So we should always make it like the general. We can't make it like, because I factored the pi, the
Oh, you are
pi.
not wrong. You are not wrong if you do that. I get you. That's what you are saying. Y is equal to 3 sine. Then we can pull out 3. So we have 100 pi t minus 5 over 11 pi x. Then you change 5 over 11 to decimal. Okay, 0 point something. So you can also do it like that.
Yes, please.
Please, is there any question? Is there any question? All right. So if there is no question, this is where we end today's meeting. I'll send you other examples on this. Maybe, brainy kind of questions so that we see how you can apply whatever we've learned to solving difficult questions. Okay.
Sir,
Hello.
sir, how brainy?
Brain working.
Hey, God.
I mean, that kind of brain working questions. So I'll send it to the group so that you try your hands at them. All right. So good night to all of you. Okay. And then bye-bye.
Same to you, sir.
All right. Yo. Adjoa and Nanama,
Okay, dear.
contact me after the
Yes, sir.
class. I need to talk to
Okay.
you
Yes, please.
on WhatsApp. Contact me on WhatsApp.